When Donald Trump became president, he surprised the world with many things. But among all the debates and arguments, there was one massive project that got the entire country talking. A border wall stretching almost 3,200 kilometers, about the distance across the U.S. from Pacific Ocean in California to Atlantic coast in North Carolina, using tall steel posts nearly 30 feet high set deep in concrete, making the border feel like an almost unbreakable barrier. But here's what nobody tells you. This wasn't the first wall, and the previous attempts, they failed catastrophically. What made this one different would shock engineers worldwide. Welcome to MacroForge, where we explore infrastructure built under impossible conditions. If construction that triggers national debate fascinates you, subscribe now. What you're about to discover will change how you see borders forever. For decades, the U.S. southern border was like a door left slightly ajar. According to U.S. Customs and Border Protection, in 2019 alone, border agents recorded more than 851,000 illegal crossing attempts. That's not over years. That's 1 year. The government faced a problem spiraling out of control. To deal with it, the U.S. started building first border fences in the 1990s under President Bill Clinton. Later, George W. Bush and Barack Obama continued expanding the system, but those fences were only a few meters high, fairly easy to climb or cut through. They weren't stopping anyone determined enough. By 2016, Donald Trump turned the wall idea into a major political message. He wanted something huge, strong, stretching thousands of miles. At first, he pushed for solid concrete wall, but Department of Homeland Security rejected the plan. Why? It would stop patrol agents from seeing what was happening on the other side. In the end, final design used tall steel posts known as bollards, strong, high, see-through. This became the main model for the border wall we see today, but building it would prove far more brutal than anyone predicted. First step in building the border wall, surveying land. The planned wall stretches almost 1,930 miles along the U.S.-Mexico border, crossing many different terrain types. Soft, sandy desert that can sink, wet clay areas near Rio Grande River, hard rocky mountains in Arizona and California that feel like natural concrete. Engineers had to measure elevation, drill soil samples, check ground stability, calculate how deep foundations needed to be in each location. This survey step was critical. It determined entire foundation design and structure of what followed. But here's where everything got complicated. The terrain actively fought construction. What worked in one location failed completely 50 miles away. Sandy areas required different foundations than rocky zones. Wet clay demanded entirely separate engineering. Every mile presented new challenges. Then came the phase that would test human endurance to its limits. To install steel posts standing almost 30 feet tall in desert, first major step was digging foundation. Sounds simple, but this was one of the most time-consuming and labor-heavy parts of entire project. Construction crews had to dig long, continuous trenches about 24 to 32 inches wide, 6 to 10 feet deep, strong enough to hold each steel post against high winds and possible damage. In areas with soft sand, excavators and bulldozers could dig trenches fairly easily. However, most of the border runs through hard, rocky terrain. Granite and sedimentary rock sit right under surface. In these places, regular digging machines were useless, completely ineffective. Crews had to use hydraulic rock breakers attached to heavy excavators, hammering and cracking rock non-stop to remove large chunks from ground. The noise was deafening. The progress, painfully slow. Rock that looked like it would break easily turned out to be harder than anyone expected, but smashing rock was just the beginning. What came next required machines nobody had used at this scale before. After trench was roughly shaped, specialized trenching machine called a trencher stepped in. These high-power machines usually run on diesel engines with 250 to 400 horsepower, allowing them to cut through hard ground at steady speed. Once excavators created first rough trench, trencher moved in to cut deeper and straighten walls. At the same time, it crushed any remaining soil and rock, leaving bottom flat and even. Conveyor system at back constantly carried loose material out of trench, keeping it clean and ready for concrete. Because trencher can cut continuously with high accuracy, it can handle hundreds of meters of trench per day. greatly speeding up construction process. But precision came at brutal cost. The machines required constant maintenance. Desert heat and dust destroyed components regularly. Breakdowns halted entire sections for days. Then came the phase where everything had to be perfect. One mistake and structural integrity failed. After trench was dug and bottom leveled, construction crew began installing reinforcing steel frame. This frame made of vertical steel bars and horizontal ties, forming long steel cage running along trench. Right after rebar frame set in place, reinforced concrete layer about 10 to 20 centimeters thick poured over it. This creates flat, stable, strong base where steel panels can be placed without sinking or tilting. When concrete bonds tightly with steel cage inside, it forms solid, continuous foundation block, greatly increasing walls' resistance to pulling forces and twisting, especially in desert where strong winds put enormous pressure on structure. But here's what engineers feared most: desert ground shifts. Temperature swings cause expansion and contraction. What seems stable today might crack tomorrow. Every foundation had to account for forces nobody could predict. Then came the moment everything depended on: bringing in the steel itself. After foundation was ready, construction site moved into very important stage, bringing in and preparing steel bollard posts, main parts of wall. These posts are actually hollow steel tubes, either square or round, about 26 feet tall with thickness of 10 millimeters. Hollow design helps reduce weight, makes transportation easier, also allows concrete to be poured inside, later making post stronger if needed. Each steel post can weigh between 250 to 400 kilograms, so they're transported from factory to site on heavy-duty trucks. Posts stacked in layers, secured with steel straps keeping them from shifting during trip. When they arrive, mobile cranes or truck-mounted cranes carefully lift each bundle off truck, place it in storage area, avoiding impacts that could bend or damage steel. Right outside work zone, temporary fabrication area set up. Here workers use high-power welding machines connecting posts into panels. Each panel usually made of 4 to 6 posts depending on wall width. Welding them into sections makes installation much faster. Instead of lifting one post at a time, crane can lift entire panel and place it directly into trench. This process requires very high accuracy. Even small mistake of few millimeters at base or at welds can cause whole panel to lean, making alignment and anchoring much more difficult. But the real challenge? That came when panels had to stand vertical. Once steel panels were welded together and brought to trench, construction site entered what many consider backbone of entire project: setting wall panels, aligning them, pouring concrete to lock them in place. This step determines how straight, strong, and long-lasting the nearly 1,730-meter barrier will be. First, large mobile cranes or truck-mounted cranes slowly lift each panel, which can weigh hundreds of kilograms, off ground. Because each panel is almost 9 meters, about 30 feet tall and long, like giant sail. Even strong gust of wind can make it sway dangerously. That's why 2 to 3 workers on ground always hold guide ropes, working closely with crane operator to position panel correctly over trench. Once panel lowered into trench, engineers begin most critical task: alignment. They use laser levels, spirit levels, tension guidelines, their own experience, making sure each panel stands perfectly vertical, lines up correctly along wall's path. Even small tilt of few degrees can cause gaps. Bending. Crooked wall, which would weaken structure and ruin appearance. After panel in exact position, workers temporarily weld its base to steel anchors or support frames already placed in trench. These welds hold panel steady while it waits for concrete, preventing it from tipping over due to wind or accidental impacts. But temporary welds weren't enough. What came next would either lock everything permanently or reveal catastrophic flaws. Right after that, concrete mixer truck or concrete pump moves to trench edge. Fresh concrete poured directly around base of panel, filling all empty space between steel and soil. Workers use tamping rods or vibrating tools, removing air bubbles, helping concrete press tightly against every surface of steel post, forming solid bond. As concrete hardens, it acts like hidden anchor, locking bottom of panel firmly into ground, greatly increasing its resistance to pulling forces. vibration, attempts to break or pry it loose. In some important areas, such as near roads or places with soft ground, crews don't just pour concrete around base of panels. They also add extra concrete layer extending about 5 feet outward from wall. This creates wider foundation pad, helping spread weight, prevents soil from eroding or sinking over time, especially after heavy rain. At same time, this wider concrete base makes it much harder for anyone to dig under wall. Instead of going through loose soil, someone trying to cross would first have to break through thick layer of concrete before reaching steel posts, making job extremely difficult and time-consuming. But concrete alone wasn't the final defense. After steel panels were set in place and temporarily secured, workers used high-pressure water hoses cleaning entire surface. This washing step removes dirt, sand, mud, oil, especially welding slag and metal fragments left over from welding process. If these materials stay on surface, paint won't stick properly. High-pressure water sprayed from top to bottom, moving along each panel, making sure surface completely clean, no residue left behind. Workers carefully follow direction of panel so water and debris don't build up in corners or gaps. Thanks to this cleaning step, anti-rust coating and protective paint applied later can stick evenly and firmly, greatly improves walls' durability and corrosion resistance. Extremely important in harsh desert environment. But there was one more layer added, the most controversial part of entire structure. At this point, wall almost complete, but one more layer of protection added on top. Normally, installation of razor wire, the sharp coiled blade wire you often see on high security fences, not done by civilian workers, instead handled by military or border patrol units. Because of high risk and security requirements, razor wire has edges sharp as razor blade, designed to cause deep cuts if someone touches it, making climbing over wall almost impossible. Coils lifted into place by specialized equipment or installed by hand depending on location. Soldiers then secure wire using metal brackets and anchor hooks, making sure it stays tight, cannot be moved or pulled aside. With this extra protection added by military, top of barrier becomes nearly impossible to climb with bare hands, greatly increasing wall's ability to stop crossings. But did it actually work? That's where numbers tell uncomfortable truths. After many years of construction, hundreds of new miles of border fencing completed, helping reduce number of easy crossing points, allowing Border Patrol to control border more effectively. According to estimates from U.S. Customs and Border Protection, total cost of wall and related infrastructure exceeded $15 billion, including materials, transportation, surveillance technology, labor. However, that number's still growing because maintenance and repairs continue costing hundreds of millions of dollars every year. Even though wall slows down and spreads out illegal crossings, cartels still found ways around it. Construction also raised concerns about environmental impacts, especially on desert ecosystem and Rio Grande River region. Many experts argue wall affects wildlife movement and natural water flow. So while border wall provided certain benefits, it's far from perfect barrier, and struggle along border continues. America built barrier to keep people out, but Japan had to stop something much more powerful, not humans, nature itself. Japan faces terrifying power of tsunamis. After suffering some of most devastating tsunamis in modern history, Japan built one of the largest coastal defenses on Earth. Massive seawalls stretching hundreds of miles along coast. These towering barriers weren't designed to keep people out. They were built to stop walls of water rising higher than buildings, destroying entire towns in minutes. The 2011 tsunami caused great loss to Japan, so country built nearly 250 miles of tsunami defense walls, each 45 to 50 feet tall, with foundations plunging 80 feet deep. Concrete Great Wall designed to buy precious minutes for people to evacuate before waves arrive. More than $12 billion invested, not only in building walls but also upgrading emergency alerts and evacuation routes. Nearly 400-kilometer stretch runs along Tohoku coastline in northeastern Japan, region that took full force of 2011 tsunami. Extends continuously through prefectures of Aomori, Iwate, Miyagi, and Fukushima, forming longest and most unified coastal defense line in Japan's history. Once exact route finalized, crews began clearing area, removing old houses, damaged infrastructure, power lines, pipelines. At the same time, they built access roads, material yards, crane platforms, concrete mixing stations, temporary drainage systems, so construction could continue even during rainy season. Much of Tohoku coastline sits on weak sandy soil, so engineers first drilled detailed surveys, reinforced ground. They installed deep concrete or steel piles, added layers of crushed stone and compacted sand, stabilized surface. Goal was creating solid base strong enough supporting wall tens of meters tall, without sinking, sliding, cracking over time. Once soil stabilized, excavators dug massive foundation pits, in some sections going more than 20 meters deep. Near shoreline crews built temporary retaining walls or coffer dams keeping seawater out. After that base layer of concrete poured, followed by dense steel reinforcement cages, large foundation blocks forming extremely heavy and wide foot, preventing wall from being pushed over by powerful waves. Above foundation, workers assembled tall, thick rebar cages based on optimized lab design, formwork set in place, concrete pumped into mold section by section, each block usually several dozen meters long, poured, cured, inspected, then connected to next, creating one continuous barrier along coast. On ocean-facing side, crews installed special concrete units, tetrapods, dolos, other energy-dissipating blocks, stacked in multiple layers around base of wall, breaking wave force before it hits structure. Some sections also use stepped faces, slope surfaces, splash reduction ledges, lowering height of water surges. On landward side, soil and crushed rock added along with drainage channels, preventing rainwater from pooling behind wall. Many stretches include walkway or inspection road on top. In some towns, seawall even doubles as part of local roadway. Railings, fences, safety ladders, signage added, allowing safe public access. In some sections where seawall needed extra thickness and impact resistance, crews added layer of precast concrete blocks onto outer surface. These interlocking panels lifted into place by crane, arranged in tight uniform pattern, strengthening wall, reducing erosion from constant wave action. Once secured tiles created reinforced armor layer, helping seawall withstand decades of pounding from Pacific Ocean. America building border wall stretching 3,200 kilometers using steel posts 30 feet tall, weighing 250 to 400 kilograms, set in concrete foundations 6 to 10 feet deep, costing over $15 billion US, while Japan constructing tsunami defense walls spanning 400 kilometers, reaching 45 to 50 feet tall with foundations 80 feet deep, investing $12 billion US. Both proving walls aren't just barriers. They're statements about what societies fear most and how far they'll go protecting against those fears, whether stopping people or stopping ocean. What amazed you most? The scale, the cost, the engineering? Drop thoughts below. Thanks for watching Macro Forge, where walls tell stories about the forces that built them. See you in the next one.